When resources run scarce, whether in a lifeboat at sea, a spacecraft off course, or a disaster zone, the question of survival becomes a matter of mathematics. Every calorie of food, every drop of water, every unit of stored energy must be stretched to last as long as possible. At first glance, the problem seems simple. Divide what you have equally among survivors and hope for rescue. But mathematics reveals a deeper challenge. The way you ration can significantly alter survival time, depending on how human physiology interacts with resource distribution. Isn't it striking that survival itself can be optimized like an equation? Calories provide fuel for the body, but the minimum needed is not fixed. A person at rest requires far fewer calories than one exerting themselves, and the body can adapt by slowing metabolism under starvation conditions. Models of rationing must weigh whether to spread food evenly across all individuals or concentrate it to maintain the strength of a few who can work, signal, or seek rescue. Too little energy for everyone risks collapse. Too much for one risks inequality and conflict. Mathematically, this becomes an optimization problem. Maximize the probability of group survival given the trade-off between fairness and efficiency. Isn't it unsettling that survival strategy may demand unequal shares? Water is even less forgiving. Humans can live weeks without food, but only days without water. Here, rationing strategies become more rigid, since dehydration quickly impairs decision-making and physical function. Environmental factors complicate the math. Hotter conditions raise the minimum requirement, while shaded rest lowers it. Some survival models propose dynamic rationing. Distribute water based on activity level and temperature, recalculating each day to prevent critical deficit. In effect, survival planning becomes a fluid equation, constantly adjusting inputs against losses. Energy, in the form of fuel or batteries, is the third variable. It powers cooking, purification, heating, and signaling. Using it too quickly risks waste, but hoarding it can mean lost opportunities to signal for help or sterilize water before disease spreads. Mathematically, this resembles game theory. Every choice involves weighing short-term survival against long-term chances of rescue. How do you decide whether to burn the last flare today or wait until tomorrow when probability curves shift? A lesser-known insight is that survival rationing often involves nonlinear thresholds. A small amount of food may drastically reduce mortality compared to none at all, but doubling that food does not double survival time. Similarly, distributing just enough water to avoid dehydration has far greater impact than slightly boosting caloric intake. Mathematical models show that prioritizing critical thresholds first, hydration over calories, signaling over comfort, extends group survival more effectively than proportional sharing. Could it be that survival is less about fairness and more about hitting these physiological tipping points? The paradox is clear. Rationing feels like an ethical question, but in crisis, it becomes a mathematical one. Equations of probability, optimization, and physiology dictate how long a group can endure. Yet no model can remove the human element. Fear, cooperation, or conflict often override cold calculation. So we are left with a haunting question. Is the best rationing strategy the one that maximizes survival time, or the one that preserves human dignity, even if survival odds fall? Rationing emerges when critical resources such as calories, water, and energy are scarce. Survival depends not just on total amounts, but on how they are distributed over time. Too much use early shortens endurance, while overly strict conservation risks physical collapse before rescue. The mathematics of rationing treats survival as an optimization problem under constraints. Models account for metabolism, hydration, exertion, and environmental conditions. By quantifying needs and supplies, one can maximize survival probability. This requires balancing immediate function with long-term preservation. In essence, rationing is applied survival calculus. Shipwreck survivors who consumed all their rations early often perished, while those who spread them carefully lasted weeks. It is like budgeting money. Send too fast and you go broke. Save too much and you cannot meet daily needs. The human body requires a baseline energy intake to maintain vital functions even at rest. This basal metabolic rate, BMR, depends on weight, age, and sex, but averages 1,200–2,000 calories per day. Rationing calories below BMR slows metabolism, conserving energy but weakening physical strength. Extended deficits lead to muscle breakdown and impaired immunity. In survival, the aim is not comfort, but sustaining core physiological processes as long as possible. Mathematical models adjust calorie allocation to balance weight loss against endurance. Each calorie is treated as survival currency. Arctic explorers survived on as little as 1,000 calories per day by minimizing exertion, though at great physical cost. It is like running an engine on low fuel. It works, but at reduced performance. Unlike food, water has strict limits for deprivation. The body loses fluid through sweat, breathing, and waste, requiring constant replenishment. Average needs are 2–3 liters daily, but rationing may reduce this to survival minimums of 1 liter or less. Mathematical survival models calculate water loss relative to temperature, humidity, and activity. Prioritizing hydration often matters more than calories, since dehydration can kill within days. Water allocation strategies extend survival by minimizing exertion and managing fluid balance. Hydration curves dictate rationing more tightly than food supply. Desert survivors often survive weeks without food, but only 3 to 5 days without water. It is like oil in a machine. Without it, the system grinds to a halt regardless of fuel reserves. Survival models must account for the trade-off between exertion and resource use. Walking long distances burns calories and water rapidly, but may increase chances of rescue. Remaining stationary conserves supplies, but risks never being found. Mathematics can estimate optimal exertion thresholds based on available rations and rescue probability. Calculations often favor minimal exertion, except in high-probability rescue scenarios. Conserving energy extends resource lifetime dramatically. Effective rationing requires aligning consumption with survival goals. A hiker lost in the wilderness survived longer by staying put and signaling rather than expending energy wandering. It is like playing chess. Sometimes the best move is to wait, not to act. Fixed daily allotments are simple, but not always optimal. Dynamic strategies adjust intake based on conditions such as heat stress, workload, or illness. Mathematical models use adaptive algorithms to balance short-term need against long-term supply. This ensures resources are used efficiently without waste. For instance, water rations may increase during exertion, but tighten on rest days. Flexibility enhances survival probability compared to rigid schedules. The mathematics resembles dynamic programming applied to survival. Military survival manuals recommend rationing more strictly when resting and allowing higher intake during forced marches. It is like adjusting sails on a boat. Resources must be matched to shifting winds and currents. Survival scenarios often involve uncertainty about rescue timing. If rescue is certain in 3 days, rationing is simple. If it could be 3 weeks, strategy changes entirely. Probability models estimate optimal allocation based on expected rescue distribution. Risk tolerance influences choices. Gamble on short survival for comfort or hedge for longer endurance. This probabilistic dimension makes rationing a decision under uncertainty. Mathematics helps quantify trade-offs between immediate well-being and long-term survival. Every sip or bite becomes a bet on the future. Lifeboat ration manuals calculate survival for 7, 14, or 21 days based on likely shipping lanes. It is like playing poker with your own life as the stake. You must decide how long to stay in the game. Models must respect hard biological limits beyond which survival collapses. Below certain calorie intakes, muscle loss accelerates irreversibly. Below hydration thresholds, kidney failure and heat stroke occur. These nonlinear points mean rationing strategies must avoid falling off cliffs of survival capacity. Energy and water reserves in the body act as buffers, but are finite. Rationing math therefore integrates both continuous and threshold effects. Staying just above collapse limits maximizes endurance. Survival is a balance on a razor's edge. Survivors in concentration camps lived for weeks on starvation rations, but collapsed once critical thresholds were crossed. It is like flying a plane just above stall speed. Safe if balanced, catastrophic if tipped too far. When resources are shared among groups, rationing becomes a social as well as mathematical problem. Equal distribution promotes fairness, but unequal allocation may maximize group survival if some members have higher rescue value. Decisions about who eats or drinks more involve ethics layered onto optimization. Group dynamics often complicate purely mathematical solutions. Cooperation can extend survival, but conflict can waste resources. The mathematics of rationing becomes entangled with psychology and morality. In such cases, numbers alone cannot decide. In lifeboat cases, stronger members were sometimes given more rations to row, a decision both pragmatic and controversial. It is like allocating fuel on a sinking ship. Who gets it determines not just survival, but fairness. The paradox of rationing is that survival depends not only on conserving resources, but on using them strategically. Hoarding too much can weaken the body beyond recovery, while consuming too much too soon shortens endurance. The mathematics shows that optimal survival lies between extremes, yet uncertainty and human psychology often drives irrational rationing choices. Scientific allocation can maximize time, but decisions under stress rarely follow equations. The paradox is that survival is both a biological and a mathematical challenge. Numbers guide, but instincts decide. Survivors often reported regretting consuming too much early or saving too much late, both errors costing lives. It is like walking a tightrope. Lean too far in either direction, and balance is lost.